This video will focus on the trend for ionization energy, both what the trend is, why it is that way, and how to explain the discrepancies within the trend. So a reminder, ionization energy is the energy it takes to remove an electron from an atom. Specifically, we're looking at the first ionization energy, so the energy associated with removing the first electron. If you look at the graph, you'll notice that the trend in general, going across a table, so like from lithium to neon and from sodium to argon, goes up. So across the table, ionization energy increases, and then going down a group, so like from helium to neon to argon to krypton to xenon, and etc. So going down a group, you notice ionization energy decreases. So the trend is going across the table, ionization energy increases, and going down the table, ionization energy decreases. So across a period, increase, down a group, decrease. The reason why it happens this way is across a table, so across a period, we have an increase in nuclear charge, which means we have more effective nuclear charge in the nucleus, which means it's pulling electrons stronger, which means we need more energy to remove an electron, which is what ionization energy is measuring. So as I pull more across a period, it becomes harder to remove an electron and a larger ionization energy. Going down a group, the effective nuclear charge decreases because of an increase in electron shielding. So going down a group, each subsequent atom adds another full energy level, which means I increase the repulsion of electrons due to that full shield between the nucleus and the outer electron, which means now there's less attraction from the electrons to the nucleus, and thus it's easier to remove the electron. Now the other thing about ionization energy, though, is something called a discrepancy. And a discrepancy is a place within the trend where the trend doesn't happen. So ionization energy increases across a period, except where it doesn't. And you'll notice within period 2, for example, so from lithium to neon, there's 2 locations where the graph zags down instead of continuing up. So it goes like up, up, down, and then up, 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 and then down, and then up again for a little bit till it hits neon. So those little points where I'm progressing forward, but I'm decreasing in ionization energy, those are the discrepancy points. And if you notice, for each period, those discrepancies exist. In general, from left to right across a period, my ionization energy increases. But there are areas where they decrease. If you look at a graph and look at where those locations are, you'll see that the discrepancy happens as I move from an S to a P. The ionization energy goes down, and then when I move from a half-filled orbital, so P3 to P4, it also goes down. If you're down into period 4, you'll see that that discrepancy happens not quite from the S to the P now, but instead the D to the P, zinc to gallium. But then we again have that discrepancy from P3 to P4. So what this means is the electron that I'm putting into P1 takes a little bit less energy to remove than that S2 electron. Or the electron I'm putting into P4 is a little bit easier to remove or needs less energy than the P3 electron. The reason why it's this way is because of orbital theory. So when I move in the S to the P orbital, I'm going to a higher energy level, which means I should have less attraction to my nucleus because I'm farther away, right? I'm at a sub-level that is higher in energy than the one before it. So it's going to take a little bit less energy to remove that one electron than it was before. The reason why at P3 to P4 we also see a discrepancy is that whole degenerate half-filled orbital versus paired up. So once I have 3 electrons all spinning in parallel in my degenerate orbitals, which is how they fill, remember 1 per orbital before they pair up, those 3 being like that have a degree of stability that when I put a 4th electron in and have to pair one set for the first time, it kind of throws off the balance. That electron-electron repulsion actually pushes those electrons out a little farther than they would be otherwise, which means that electron becomes a little bit easier to remove. So the first discrepancy is due to going from a full energy level a full sub-level to a non-full sub-level, and that non-full electron is easier to remove. And then the other one is from a half-filled to putting one more in that half-filled, and that next one that you're putting into your first paired orbital is a little easier to remove. That's it in terms of ionization energy trends, discrepancies, and whys. Have a nice night.